This lesson is about symmetries and transformations of graphs. First, we'll talk about symmetries. Here we have examples of some symmetries that may happen with the graphs. On the first diagram, we see y-axis symmetry. What does it really mean? Well, if you have a point that belongs to the graph, then the point that is perpendicular reflection in y-axis also belongs to the graph. So if point xy belongs to the graph, then if you change the sign for x, negative xy will also belong to the graph. Second example is symmetry in x-axis. So this time if we have a point that belongs to the graph xy, and if we change the y value to the opposite, which means look for a point symmetrically to the other side in respect to the x-axis, then we get a point that also belongs to the graph. So point x, negative y also belongs to the graph. On the last diagram, we have central symmetry. It's a symmetry about the origin. So if we have a point xy that belongs to the graph, and if we change both coordinates into opposite, negative x and negative y, then such point will belong to the graph as well. So we reflect this point in origin to the other side by the same distance. Similarly, this example shows the central symmetry in the origin. Okay, so when we see graphs, it's kind of easy to detect if the graph is symmetrical or not. However, sometimes we don't have a graph, we have just the formula for the function. How can we determine if a function is symmetrical about the y-axis, about the x-axis, or in the origin, or maybe not at all? We have the following definitions. If we have equation of a function y equals f of x, and we can show that f of negative x is actually the same as f of x, then we can talk about symmetry in y-axis, and we'll mark S with the subindex y. So symmetry in y-axis means that the value for particular x and negative x will be the same. F of negative x equals f of x. Such a function is called even. The second type of symmetry, symmetry in x-axis, can be checked by replacing y by negative y, and the resulting expression as a function of y gives us the same value as the original expression with just y. That we have a symmetry as x, and on the diagram it looks like this. If I have the same value x for y and for negative y, then we can say that such a relation, because that can't be a function anymore, such a relation is symmetrical in x-axis. And the last type of symmetry that we'll be interested in is the central symmetry, symmetry in the origin, SO. So a function f of x is symmetric with respect to the origin if and only if, when we replace x by negative x, the value of the expression becomes opposite to the expression of f of x. So we can actually pull this minus outside of the function and these two expressions will be equal. And such functions are called odd. On the diagram, it looks as follows. If I have a value for specific x, and it's here, this is f of x, then the value for negative x will be exactly the same as for x, except that with opposite sign. So it will become here negative f of x. So value of negative x is equal to negative f of x. Therefore, if we have a function in explicit form in equation like this, y equals some sort of formula of x, the easiest way to check if this function is even or odd is just to calculate what's f of negative x. If f of negative x is the same as f of x, then the function is even. If it's opposite to f of x, then the function is odd. If it's neither of these, then the function is neither even nor odd. If we deal with a relation, not a function of x, but just a relation, we can also check if replacement y by negative y will produce the same equation. So here we have the first exercise. without graphing, determine symmetries of graphs of the given equations. Okay, the first one is really an explicit function. It's a polynomial of 4th degree. Since both of the exponents are even, we may predict that this function would be even, but let's check it. So we need to find what's y of negative x. Well, if I plug it in negative for x and raise it to the even exponent, then this is really the same as just x to the same exponent, because negative to the even becomes positive anyway. So that's really the same as y of x. Therefore, y is even. It's also easy to check that replacing y by negative y make the equation different than the original one. So we don't have any other symmetry. We have only symmetry in y-axis. So y is even and we have symmetry in y-axis. The second equation represents still a function, and it's a polynomial of odd degree. So we may predict that this will be odd, but let's check. So we need to check what's y of negative x. If I plug it in negative x for x and cube it, or negative x here, then negative x cubed is the same as negative x cubed without the bracket, and that becomes positive x. Well, can I rearrange this expression so I can actually see the original function y of x? Yes. As soon as I pull the minus out of the bracket, then whatever is inside represents the original function. So this is really equal negative y of x. My function of negative x is the same as negative y of x. Therefore, y is odd. And we have a symmetry in the origin. And again, observe that if we would like to change just y for negative y, that wouldn't produce the same equation. Therefore, we don't really have symmetry in x-axis. Also, as soon as we know that something is a function like the first or second example, then we can't really talk about symmetry in x-axis, because that would make it not a function unless our function is actually just a constant 0. The next example is written in a relation form, so what we really need to do is check all three cases. If we use negative x instead of x, then our equation becomes negative xy equals 8, which is definitely not equivalent to the original equation xy equals 8. So we have no symmetry in y-axis, which means that this relation is not even. Now let's check the other possibilities. If we replace y by negative y, again we have negative xy equals 8, and again it's not the same as the original equation, so we have no symmetry in x-axis. Do we have symmetry in origin? Well, we need to replace both negative x instead of x and also negative y instead of y. Both of these replacements. So now, yes, we have negative x times negative y, which is 8, and yes, this is equivalent to the original equation xy equals 8. So yes, we have symmetry in the origin. That means that the relation is odd. And the next relation, again, we want to ask ourselves, do we have symmetry in y? Do we have symmetry in x? Or do we have symmetry in the origin? To check symmetry for y, we replace x by negative x. So if I use negative x instead of x, I have negative x squared plus y squared equals 9, which obviously is the same is equivalent to the original equation x squared plus y squared equals 9. So yes, we have symmetry in y-axis. To check symmetry for x-axis, we're going to replace y by negative y. So similarly as before, x squared plus negative y squared equals 9. Yes, it is equivalent to the original x squared plus y squared equals 9. So yes, we have symmetry in x-axis. Well, what about symmetry in origin? If we replace both x by negative x and y by negative y, then, as you may expect, since we're squaring those negatives, the resulting equation is really equivalent to the original equation. Therefore, yes, we also have symmetry in the origin. Well, and that's not a surprise because this equation is actually an equation of a circle. So in a system of coordinates, it's a circle with radius 3 and the center 0, 0. So yes, this circle is symmetrical in x-axis, in y-axis, and also in the origin. So this particular relation is actually even, odd, and also we have symmetry in x-axis. And two more examples. This one is again a relation, it's not a function. We can check as before, do we have symmetry in y-axis? Well, we replace x by negative x, so we have negative x equals absolute value of y plus 1, which is definitely not the same, it's not equivalent to original x equals absolute value of y plus 1. So we don't have symmetry in y-axis. Check symmetry in x-axis, which means replace y by negative y. So we have x equals absolute value negative y plus 1. Oh, this time, since absolute value of negative y is the same as just absolute value of y, so yes, it is equivalent to the original equation. So yes, we have symmetry in x-axis. And also check symmetry in the origin by replacing both x and y. But now you can probably expect what the answer would be. This is definitely not equivalent to the original equation, since this is actually equivalent to the equation negative x equals absolute value of y plus 1, which is not the same as the original one. So we don't have symmetry in the origin. So here the answer is we have only symmetry in x-axis. And the last example, this time we deal with a function, so there's no need for checking symmetry in x-axis. We can just check symmetry in y, that means if the function is even, or symmetry in the origin, that means if the function is odd. To check symmetry in y, we calculate y of negative x, meaning we replace x by negative x, so we end up with something like this. Well, this is definitely not the same as absolute value of x plus 1, which is y of x. Since these two are not equal, therefore we don't have symmetry in the y-axis. To check symmetry in the origin, it's enough to compare y of negative x and negative y of x. Since negative y of x is negative absolute value of x plus 1, which is not the same as just absolute value of x plus 1, so it's not the same as y of negative x, which was here. These two guys are not the same, therefore we also don't have symmetry in the origin. So y is neither. It's not even and it's not odd. Not even nor odd. In the next example, we're supposed to graph each relation and also state its domain, x and y intercepts, and possible symmetries that we can find. So the first example is y equals square root of absolute value of x. Since absolute value of x is always bigger equal 0, this is always bigger equal 0, there's no problem with root. Therefore, the domain of y is actually all real numbers. Now we can check symmetries. What about y of negative x? Well, if I plugged in negative x instead of x under the absolute value, this really becomes the same as absolute value of x, which is y of x. That really means that y is even. Okay, what is this function? How does it look like, for example, if we drop absolute value? Well, dropping absolute value means considering two cases. If x is bigger equals 0, then we can just drop the absolute value. We have square root of x. We know very well how square root of x looks like. It starts from 0, then go 1, 1, and 4 square root of 4 is 2. So the shape looks somehow like this. The other branch, if x is actually negative, then to drop absolute value we have to switch the sign, so we end up with square root of negative x. Then this minus by the x really causes that this part of the graph will be reflected to the other side in y-axis. And this is not a surprise since the function is even. So whatever we see to the right, we should see to the left of y-axis. Exactly symmetrical shape. So we have even function. And x and y intercept equals just 0, 0. That's the only point. Okay, the next example is not a function, it's just a relation, but we can still talk about domain. In this case, maybe before we state the domain, we'll investigate some numbers that actually satisfy this equation and we'll try to see the graph. So how can we approach this example? First of all, absolute value causes that no matter if we change x into negative x or y into negative y, or both of them into negatives, the equation will be the same. So we actually have symmetry in x, symmetry in y, and central symmetry in the origin. Wow, so that's pretty symmetric shape. Now let's check some points and try to make sense how this relation looks like. Let's keep y 0 for now. So if y is 0, x is either 4 or negative 4 to satisfy the equation. So it's plus minus 4. We already have 2 points, we can graph it. Negative 4, 0 and 4, 0. So those are x-intercepts. Well, let's do the same with y-intercepts. If x is 0, then what the y could be? For similar reason, y could be plus or minus 4. So we also have these points. Negative 4 and plus 4. Okay, let's change something for x and y. Let's say if y is plus or minus 1, which result in absolute value being 1, then to add to 4, I need 3 for x. So x could be plus or minus 3. Oh, I have already 4 points to plot. So plus 3, 1 and negative 1, and minus 3, 1 and negative 1. Similarly, if we increase y by a little bit, I have to decrease the x by the same much. So if this is 2 plus or minus, then the x could be plus minus 2 as well. So we have those points. Oh, we start seeing some pattern. So if y is plus minus 3, then the x will be plus minus 1. Here we definitely see a strong pattern that looks like a diamond if you connect all the points, straight pieces of line. And we have a diamond like this. It's very symmetrical. So now it's easy to state the domain for this relation. It is everything from negative 4 up to 4. Let's put some numbers on this graph as well. The following example, that's a cubic function. We already experienced this function. It is odd since y of negative x is actually equal negative y of x. So y is odd. So if I know the shape to the right of y-axis, I can flip it over the origin to the other side and have the remaining part of the graph. How to graph it with no graphing calculator and not too much of calculating particular points? Well, first of all, I would suggest that we factor this polynomial, because by factoring it, we can actually see all the roots. That's the factored form. So the roots are 0, -1, and 1. Okay, -1, 0, and 1. So those are also x-intercepts. Do we have any y-intercept? Well, if x is 0, then y is 0. So the only y-intercept is 0, 0, of course. And x-intercept is 0, 0, -1, 0, and 1, 0. Now the domain of it is all real numbers, because it's just a polynomial. In order to finish the graph, maybe we can check a couple more points. So, table of values. If x is 2, then I have 8 minus 2, which is 6. Okay, for 2, I have already 6 somewhere there. So it looks like it goes pretty steeply up. And maybe let's check 1/2. If x is 1/2, then I have 1/8 minus 1/2. So it's -3/8. So here we have a little bit less than half, approximately here. We can already volunteer a shape. We know the cubic function is a snake shape, and this part of the graph will be reflected to the other side in similar manner. So it will look somehow like this. Okay, so that's our function. This is 1, and that's 1. And the last example. This time we have a radicand, so to find the domain we really need to solve inequality 9 minus x squared must be bigger equals 0. Okay, if I bring the x squared to the other side and take square root on both sides, remember that square root of x squared is absolute value of x, and square root of 9 is just 3. So inequality absolute value of x is smaller than 3 means that x oscillates between -3 and 3. Therefore, the domain of our function is from -3 to 3. Now, is this function even or odd? So we need to find out, is y of -x the same as y of x or the same as -y of x? Well, if I plug it in -x for x under the square will annihilate it, and you really end up with the same as original y of x. So that means that y is even. Okay, let's try to graph it. In order to actually see the shape a lot better than in this form, I would suggest to square both sides of the equation. Y squared equals 9 minus x squared. And then when you bring the x to the other side, you end up with the regular equation of a circle with center 0, 0 and radius 3. So yes, we are ready to graph. We start with -3 to 3, that's our domain. And the y-intercept, when you place x equals 0, then y becomes 3. So it comes through 3, it confirms the idea of the circle. However, since y is positive, it's only the top part of the circle. So it's top semicircle like this. In order to get the bottom semicircle, the equation should have a minus in front of the root. Otherwise, it's a top. Here's an interesting question. Find a function that is both even and odd. Well, we had relations that are both even and odd. For example, this one or a circle. But now we're looking for a function that is both even and odd. That wasn't a function. If the function is both even and odd, that means if a point belongs to such function, let's say choose this point, then since it's even, the point with opposite x coordinates should belong to this function, and since it's odd, the point with both coordinates opposite should belong to the function, which really means that we wouldn't have a function, since this vertical line will contradict the definition of function. it crosses the graph twice. So when this is possible? Only when this point is actually with y-coordinate 0. So we can't have any point that belongs to such a function and has y-coordinate different than 0, because it led to contradiction. Therefore, all points that belongs to this function should be on the x-axis, should have y-coordinate 0. Therefore, such a function must be a constant function 0. So f of x is equal 0. That's the only function that satisfies these two conditions. Otherwise, if we have a function and we check that it's, for example, odd, we don't need to check that it's even, because it can't be both, unless it's 0. Or if we check that the function is even, we don't need to check for being odd. However, with relations, we need to check all three types of symmetries.